To discover an alien planet 50 light years away, astronomers don't just need a bigger mirror or a more sensitive camera. They actually need a perfectly flawless microscope slide.
Right, which sounds crazy, but it's true.
Welcome to the deep dive. Today we are tailoring our entire analysis specifically for you, the two-photon lithography expert. You spend your career operating at the absolute microscale. You're optimizing voxels, characterizing photopolymer resins, and probably fighting with the z-axis on your lithography systems every single day.
Oh, constantly fighting the z-axis.
Exactly. But today, we're taking your daily reality and applying it to the largest possible macroscale. We're going to look at how the exact same 2pp hardware sitting in your lab is currently acting as the fundamental bottleneck for, well, humanity's ability to image temperate, Earth-like exoplanets.
Yeah, and we are pulling this from a really fascinating February 2026 astronomy paper. It details the first on-sky demonstration of a highly advanced optical system called the PIAACMC.
That is quite the acronym.
It really is.
Yeah.
They tested this using the MagAO-X instrument on the 6.5-meter Magellan Clay telescope down in Chile. And basically, the researchers needed to physically block out the blinding light of a host star so they could actually see the incredibly faint light reflecting off an orbiting planet.
And to do that, they had to build a microscopic, phase-shifting optical mask. So our mission today is to unpack exactly how this revolutionary starlight blocking technology operates at the waveform level.
Right.
And then we'll dive deep into the very familiar and honestly probably very frustrating manufacturing challenges the team at Leiden University faced when they tried to print this mask using an older generation nanoscribe system.
Oh, yeah, the hardware definitely fought them on this one.
It did.
Yeah.
We want to look at why the hardware fought them, how they tried to hack around it, and what this all means for the future of astronomical observation.
Because, when you trace the photon's journey all the way from a distant solar system down through the telescope's optics, the final resolution, the actual ability to see the planet, is quite literally at the mercy of your 3D printer's calibration.
It's wild to think about, but before we talk about the microscopic 2pp structures, we have to understand the astronomical problem they're trying to solve. Because in high contrast imaging, they are fighting against dynamic ranges that just completely break standard optical sensors.
Yeah, it's a massive physics hurdle.
Yeah.
So if you want to find an Earth-like planet, something temperate that could potentially host liquid water and life, you have to look at it in reflected light.
Right.
But a star is just unimaginably brighter than a tiny rocky planet. If you have an Earth analog orbiting a sun-like star, the contrast ratio is 10 to the negative 10.
Wait, 10 to the negative 10?
Yeah, exactly.
So the star is 10 billion times brighter than the planet.
10 billion, yeah. So in any standard optical system, the photons from the star just completely saturate the sensor, and the planet's signal is utterly lost in the noise. It's a dynamic range nightmare.
Which is why, historically, astronomers use coronagraphs to physically block the starlight, right?
Exactly. But traditional coronagraphs have some pretty severe limitations. They often rely on essentially placing a physical opaque block in the focal plane to eclipse the star.
Like holding your thumb up to block the sun.
Yeah, but the problem is diffraction. When light hits a hard edge like that, it diffracts, creating a series of bright concentric rings around the central spot.
And that central focus spot of light from a perfect lens is what optical physicists call the airy core.
Right. And those diffraction rings spreading out from the airy core totally ruin the contrast. So to mitigate that, traditional systems use a technique called apodization.
Okay, let's unpack this. Apodization.
Yeah, so they essentially soften or restrict the edges of the telescope's pupil to suppress those diffraction rings. But standard apodizers do this by physically absorbing or blocking light at the edges of the aperture.
Oh, so you end up throwing away a massive percentage of your precious incoming photons.
Exactly. You're losing light you desperately need. And worse, these older coronagraphs have a large inner working angle.
The inner working angle, or IWA, that's the absolute closest you can look to the star before the coronagraph itself starts blocking the planet's light.
Right, because your thumb, in this analogy, is too big.
Yeah, sure, it blocks the sun, but your thumb is so big it also blocks the airplane flying right next to the sun. And if you're looking for an Earth analog, the planet is orbiting incredibly close to its host star.
Which means if your chronograph's inner working angle is too wide, you completely blind yourself to the habitable zone.
That's a huge problem.
It is. Which is why the astronomical community has been chasing the theoretical limit of a perfect coronagraph for years. A system that blocks the star, preserves 100% of the planet's light, and can look incredibly close to the optical axis.
And that theoretical limit is approached by the system we're discussing today, right? The PIAACMC, meaning phase-induced amplitude epitization complex mass coronagraph.
It is a total mouthful.
It really is. But the performance claims are staggering. I mean, it promises nearly 100% throughput and a sub-lambda over d inner working angle, meaning it can resolve a planet that is closer to the star than the standard diffraction limit of the telescope itself.
Yeah, but to achieve that, the light has to be manipulated in ways that are almost counterintuitive.
Right. So to understand why the 2PP manufactured mask is so vital, we have to trace the chaotic journey of light through the PIAACMC system.
Yeah, let's trace the optical path through the MagAO-X instrument, because this explains why the incredibly precise mask is required. The first thing the incoming starlight hits is a set of forward PIAA lenses.
And these are highly complex aspheric lenses that perform lossless epitization.
Precisely. They geometrically remap the light. Instead of blocking the edges of the pupil to soften the diffraction rings, these lenses physically bend the incoming uniform wavefront. They redistribute the light from the outer edges and concentrate it toward the center.
Okay, so they create a bell curve-like intensity profile perfectly designed to null the star without losing a single photon.
Right, but there's a massive optical trade-off here. These forward PIAA lenses are optimized exclusively for light coming straight down the optical axis, the star's light.
But the exoplanet we want to see is slightly off-axis.
Exactly. So when the planet's light hits those exact same remapping lenses at an angle, it gets severely distorted.
The paper describes it as getting warped into a shape that resembles a pineapple, which is just, it's such a funny image.
It really is. You take this perfect little point source of planet light, and the PIA lenses stretch it out into an airy core with a bizarre asymmetric tail pointing back toward the optical axis.
It's like a funhouse mirror. The forward lenses are a funhouse mirror that perfectly warps the light.
It's a chaotic distortion, yeah, but it's a calculated sacrifice for the absolute heart of the system, which is the focal plane mask. After the light is remapped by the forward lenses, it hits this mask.
And this is where the system completely deviates from traditional coronagraphs.
Yeah.
The mask isn't an opaque disk. It doesn't absorb or reflect the starlight at all.
No, it's a fully transmissive, phase-shifting optical component. The starlight passes right through it. What's fascinating here is that it uses the light to destroy itself.
I love this part.
Yeah, as the on-axis starlight passes through the physical material of the mask, the topography of the mask actually slows down the wavefront. By strictly controlling the physical thickness of the material at a submicron level, you can delay the light waves just enough so that when they emerge, they are perfectly out of phase with the rest of the light.
Destructive interference. You're actively shifting the phase by exactly 180 degrees.
Exactly. The crest of one light wave perfectly overlaps with the trough of another, and they completely cancel each other out. The star effectively deletes its own photons at the focal plane.
Meanwhile, our distorted pineapple-shaped planet light, because it came in at a slight angle, physically bypasses the central phase-shifting zone of the mask.
It sails right on through, totally untouched by the destructive interference.
So cool.
Yeah, and from there, the light hits a Leod stop, which is a physical baffle that catches any residual high-frequency diffracted starlight that managed to leak to the outer edges.
And finally, the remaining light, which is just our distorted planet light, passes through a set of inverse PIAA lenses.
Right.
So going back to the funhouse mirror analogy, these inverse lenses are a second funhouse mirror placed backwards to exactly undo the distortion of the first.
They literally unremap the light. They take that warped pineapple shape and they mathematically snap it back into a sharp, readable, perfectly focused point. You get your planet back?
It is a stunning piece of optical engineering. But the entire multi-million-dollar architecture hinges entirely on the focal plane mask perfectly phase-shifting the starlight across multiple wavelengths.
Absolutely.
Yep.
If that physical mask is off by even a fraction of a wavelength, the phase shift isn't exactly 180 degrees. Crests don't perfectly align with troughs, the destructive interference fails, the starlight leaks right through, and the planet is entirely washed out.
And this brings us right to your laboratory bench. Because to manufacture a mask capable of that level of perfection, the researchers at Leiden University couldn't rely on standard optical fabrication. They had to use two-photon polymerization.
Right. Now that we know what the focal plane mask does, we need to look at how the researchers actually built it, using the exact same tools the listener uses in their lab.
They needed to create two specific masks for the MagAO-X instrument, didn't they?
Yeah, one optimized for a narrowband filter at 875 nanometers, and a second for a broadband filter centered at 908 nanometers. And the physical scale of these masks is incredibly small. The narrowband mask has an active radius of just 45.3 microns.
Wow.
The broadband is 47 microns. That's roughly the width of a human hair.
Okay, here's where it gets really interesting. For you listening, printing something the width of a human hair is a standard Tuesday. But wait, if we're just talking about microscopic topography, why didn't they use standard 2.5D lithography? E-beam lithography or reactive ion etching are incredibly precise and widely used for micro-optics. Why force a 2pp machine to do this?
It comes down to the broadband phase shifting requirement. If you want to perfectly phase shift light across a band of different wavelengths, you can't just use flat, discrete stepped layers like you get in 2.5D etching. The mask requires distinct, continuous sub-micron height variations. It consists of 10 concentric rings, but the profile of those rings is highly complex. You need true 3D manufacturing capability.
Only the highly localized focal point of a near-infrared laser in a 2pp system can trigger the localized 2-photon absorption required to sculpt those continuous, highly precise z-axis curves into a single monolithic piece of resin.
Exactly. So they turned to the workhorse of the field, an older generation nanoscribe photonic professional GT. They equipped it with a 63x immersion objective and chose IP-dip photoresist as their medium.
And they printed directly onto a 1 millimeter thick UV-fused silica substrate.
Yep. For you listening, this setup is about as familiar as it gets. It's the standard toolkit.
But the hardware fought them. Building those continuous phase-shifting curves requires the laser to hold an absolute mathematically perfect 0 point on the glass substrate. The exact z-axis height of the polymerized voxels dictates the optical path length of the light passing through it.
And that is exactly where the nanoscribe system completely broke down.
Yeah, having established the high-stakes microprinting, we have to move into the reality of the lab and the specific hardware failure that bottlenecked the entire astronomical observation.
The researchers ran into a critical hardware failure. The paper diplomatically describes it as an unknown issue with the machine's automatic interface finder.
Oh man, any 2pp engineer knows the absolute dread of a failing interface finder.
The interface finder is supposed to be your anchor. Before printing begins, the system uses the reflection of the laser to detect the exact boundary between the substrate and the unpolymerized resin. It establishes where Z equals 0. But when printing on this specific UV-fused silica with IP dip, the autofinder just kept failing.
Let's dig into why that happens, because it's a known physics problem with these specific materials. The nanoscribe sensor relies on a stark change in the refractive index between materials to generate a clear reflection signal.
Right.
But the refractive index of the immersion oil, the 1 millimeter fused silica glass, and the unpolymerized IP dip resin are all incredibly similar at the near-infrared wavelengths the machine uses.
Exactly. There just isn't enough optical contrast for the sensor. The reflection is incredibly weak, the signal scatters, and the interface finder returns a noisy, inaccurate reading.
So the machine places the Z0 plane a few hundred nanometers too high or too low.
Which is an absolute disaster for true 3D printing. It's like trying to pour the microscopic foundation of a skyscraper, but the bedrock beneath you is randomly shifting up and down by a few feet every single time you calibrate your equipment.
If your voxels are placed too high, they don't adhere to the glass and just wash away during development.
Yeah. And if they're placed too low, they embed themselves into the substrate, and the physical heights of your delicate phase-shifting rings are completely ruined.
And because the mask is a transmissive optical component, they couldn't just solve the problem by slapping a highly reflective coating onto the glass to help the sensor. The substrate had to remain optically transparent.
They were totally trapped.
So how do you print a sub-wavelength optical mask when your highly advanced laser system literally doesn't know where the ground is?
Brute force. Yeah. Since it was impossible to define a repeatable, optimal Z offset automatically, the team resorted to manually guessing. They printed the exact same mask design in massive arrays across a single substrate, but they incrementally tweaked the manual Z offset for every single print.
That's like trying to bake a masterpiece wedding cake with a broken oven thermometer. You just bake 10 cakes at random dials and pray one is perfect.
That is exactly what they did. They just laid down dozens of masks through the substrate under a 3D laser scanning microscope, mapped the topography of every single print, and essentially just picked the one that happened to land closest to their target dimensions.
Wow, it's a monumental effort in manual calibration. I mean, for the listener, think about how much is riding on the literal calibration of your 2pp machines. But the sobering reality is that even after doing all of that, even after selecting the absolute best mask out of the entire brute force batch, the manufacturing error was still severe, right?
It was. The best masks achieved a root mean square error, or RMSE, in the Z direction of roughly 60 nanometers for the narrowband mask and 40 nanometers for the broadband mask.
Now, a 40 to 60 nanometer RMSE sounds like a triumph of micromanufacturing, but let's look at what that actually means for the optical physics of the coronagraph. That RMSE translates to an overall surface deviation across the entire mask of roughly 100 nanometers.
And in the context of near-infrared wavelengths around 900 nanometers, a 100 nanometer physical deviation is massive. It's more than 10% of the entire wavelength.
Right.
The team ran a strict tolerance analysis prior to manufacturing to achieve the deep starlight cancellation they needed. Their simulations proved they required an RMSE of just 5 nanometers, a maximum surface deviation of 10 nanometers.
Because if you're trying to induce destructive interference, the physical topography of that resin has to shift the phase by exactly half a wavelength, 180 degrees. If the physical height of the IP dip resin is off by 100 nanometers, the wavefront is delayed slightly too much or slightly too little. The phase shift might be 160 degrees or 200 degrees.
The crest of the light wave no longer aligns perfectly with the trough. They don't cancel out.
And the starlight leaks right through to the final image. The simulations showed exactly how devastating this was. With a perfect 5 nanometer tolerance mask, the theoretical contrast ratio was supposed to be 1.8 times 10 to the negative 5.
But when they plugged the actual 100 nanometer surface deviation of their best nanoscribe print into the model, the simulated contrast plummeted to 3 times 10 to the negative 4. They lost an entire order of magnitude of blocking power purely because of the z-axis inconsistencies during the 2pp process.
But they were out of options. That imperfect, manually hacked IP dip mask was the best they could produce with the hardware they had. So taking this imperfect mask, the researchers plugged it into the MagAO-X instrument, mounted it on the Magellan Clay telescope, and pointed it at the sky.
Yeah, they started with laboratory tests using MagAO-X's internal light source to establish a baseline. And in the highly controlled environment of the lab, it actually performed remarkably well. They successfully demonstrated the optical gymnastics of the PIAA lenses.
Right, they recovered between 92 and 97% of the off-axis light's shape, meaning the warped pineapple snapped back into a focus point exactly as designed.
And they achieved sub-lambda over D interworking angles of 0.74 for the narrowband and 0.76 for the broadband. It proved that the fundamental mathematics of the PIAACMC architecture are perfectly sound.
The raw contrast matched their simulated models of the flawed mask perfectly, hovering around 1.6 times 10 to the negative 3.
But the true test is looking through Earth's atmosphere. They pointed the telescope at a binary star system known as HD 142527.
So what happens when you put this system under the immense stress of a real-world observation?
The performance predictably dropped. On sky, the raw contrast fell to 1.4 times 10 to the negative 2 for the narrowband and 7.8 times 10 to the negative 3 for the broadband. Another order of magnitude loss.
So what does this all mean? Did the 2pp mask fail them when it mattered most? I mean, we have to be fair to the manufacturing process here. That secondary drop in performance wasn't entirely the fault of the IP dip mask, was it? Ground-based astronomy is incredibly chaotic.
Oh, far from it. If we connect this to the bigger picture, the paper explicitly details the environmental hurdles they were fighting. When looking through the atmosphere, they were dealing with severe turbulence. This caused jitter, literal high-frequency vibrations in the instrument of about 7 milliarc seconds RMS.
Right, so the starlight wasn't staying perfectly centered on the phase-shifting mask. It was microscopically dancing around it.
Exactly. And because the mask's destructive interference relies on absolute spatial alignment, any movement means the star's wavefront hits the wrong topographic zones of the resin. That immediately breaks the phase shift.
Makes sense.
Furthermore, they were battling non-common path aberrations, or NCPAs. These are tiny, uncorrectable optical distortions occurring inside the coronagraphic arm of the instrument itself. So the atmosphere jitter and the internal aberrations heavily muddied the waters during the on-sky test.
But here is the ultimate takeaway for the 2pp engineers listening right now. Even if the astronomers solved the jitter, even if they had perfectly still air, perfect adaptive optics, and zero internal aberrations, the absolute physical ceiling of that instrument is still fundamentally locked to the 100 nanometer surface deviation of that IP dip print.
Precisely. The mask is the hard floor. The team at Leiden proved that the PIAACMC concept works on sky at submicron near-infrared wavelengths for the very first time in history. It is a monumental validation of the optical theory.
But to push deeper, to cross that threshold and actually reach the extreme contrast required to directly image a temperate Earth analog, they have to solve the physical manufacturing problem.
They need a flawless mask. The quest to find a second Earth relies entirely on pushing two-photon lithography past its current functional limits.
The older Nanoscrap GT system, with its refractive index mismatch issues and discrete voxel stepping, simply cannot reach the 5-nanometer tolerances required by high-contrast astronomy.
Which leaves us with a highly provocative thought to consider. The researchers struggled with step height inaccuracies and Z-offsets on an older generation nanoscribe. But what if they didn't have to?
Right.
For the 2PP experts listening, what if this same mask was printed on the new generation Quantum X system?
Oh, by utilizing two-photon grayscale lithography.
Exactly. In standard 2PP, the laser fires at a constant intensity, and you build topographies by stacking discrete layers, which naturally introduces surface roughness and stepping errors. But with two-photon grayscale lithography, the system continuously modulates the actual power of the laser in real time as it scans.
You aren't printing layers, you're fluidly adjusting the size of the voxel dynamically.
Yeah, you can print perfectly smooth, mathematically continuous slopes and curves in a single pass. It theoretically eliminates the step height slicing issues entirely.
And with vastly improved surface-finding sensors in the newer hardware, you could potentially bypass the refractive index glitches that force that whole brute force array printing nightmare.
If grayscale lithography can consistently hit that flawless 5-nanometer tolerance on a transparent substrate, it changes the entire paradigm. It could finally give astronomers the perfect optical component they need to truly block out a distant star.
It's the ultimate engineering challenge, and it sits right in your domain. Thank you for joining us for this special custom deep dive on the 2PP podcast. The next time you sit down at your lithography system, calibrating your lasers and fighting with your surface-finding algorithms, remember that you aren't just manipulating microscopic resin. You are directly manipulating the boundaries of human observation. The road to discovering alien life doesn't just go through a telescope in Chile, it goes right through your photoresist. Keep pushing the limits, and we'll catch you on the next one.